Hello students, welcome to today's lecture on Theory of Machines. This is the part 2 of the lecture of analysis of brakes. In the previous lecture, we started the analysis of block brakes and discussed about the pressure distribution on the drum. In both the cases, 2 theta was greater than 60 degree, and also in the case when 2 theta is greater than 60 degree, like this, and also when theta is less than 60 degrees, like this. Next, we discussed about the various forces that will be acting on the drum and the block when the brake will be applied. We also learned to draw the free body diagram on the drum and the lever to which the block is rigidly fixed. We further discussed the various possible positions of the fulcrum with respect to the line passing through the point of contact of the block and the drum. Now in today's lecture, we'll discuss the various configurations of the single block brakes with respect to the fulcrum position and try to derive equations for the braking torque and the force applied at the lever. So let's take the first case. This is the same drum which is rotating in the clockwise direction, having the radius R. The radius of the drum is R. Then this is the lever which is pivoted here at point O. This is having the block which is rigidly fixed to the lever, and the force P is applied in downward direction. P is the force that is applied on the lever. Now at this point, the point of contact of the block and the drum is passing through the line is passing through the fulcrum point, right? So let's see what will happen in this case. Next, as per our discussion, let's plot the various forces. So this will be the normal reaction of the drum on the block. Similarly, this will be the radial force that is applied by the block on the drum. So N is the normal reaction. Next, we will plot the friction. So this is the friction force on the drum, which will be in the direction opposite to the direction of motion. Similarly, there will be force of friction on the block, which will be in the direction opposite to the force of friction in the drum. F is the force of friction and mu is the friction coefficient of the brake lining. So there will be a friction lining here on the block. Mu is the friction coefficient of that friction lining. And TB is the braking torque on the drum. So from the free body diagram of the drum, we can see that F is equal to mu n, and we can try to calculate the braking torque. So TB is the braking torque of the drum, and the distance of the center point from this fulcrum point is A, and the total length of the lever is L. So this distance from the center point to the point of application of the force is nothing but L minus A. Fine. So these are the construction details. Now, assuming that the normal reaction and the frictional force act at the middle point of the block. So this we have already discussed earlier. So the braking torque on the drum will be equal to frictional force into radius. Torque is equal to frictional force into radius. So the frictional force is nothing but mu into N, as seen here, and the radius is R. So the braking torque on the drum will be TB, which will be equal to mu into N into R. Now let's take moment about the fulcrum point O in this free body diagram of the lever. So we have this force N. So the moment of N about this point O will be in the anti-clockwise direction, right? You can see this. This is point, pivoted point. So force N will try to rotate this lever in the anti-clockwise direction. So what will be the moment? N into the distance of the line of action of the force N from the pivoted point. So this is the distance, that is A. So N into A will be anti-clockwise, so it will be positive. So N into A. Next, since F is passing through the fulcrum point, so the moment of F will be 0, as the distance of the line of action of the force F from the fulcrum point is 0. So this will be having 0 moment. Next we have P. So P will be rotating the lever in the clockwise direction about the fulcrum point. So the moment of force P about the fulcrum point will be the distance force P multiplied by the distance of the line of action of the force P from fulcrum point, that is nothing but L, right? P is at the distance of L from fulcrum point. So P into L, and this will be in the clockwise direction, so it will be equal to N into L. So from here we can calculate N as PL upon A. So now we will substitute this value N in this braking torque. So we'll get the final equation for the braking torque as TB is equal to mu PL R upon A, right? So this is how we carry out the analysis of brake to calculate either the braking torque or the load applied P. P can also be calculated from here. Next we'll see a different configuration where the line from the point of contact is not passing through the fulcrum point. It is somewhat at a distance of B from the fulcrum point. So let's see. We'll again take the same drum which is rotating in the clockwise direction. Now it is the lever and this is the block. The force P is applied in the downward direction, and now you can see that the fulcrum point is at different position. So this is the central line of the block and the drum. Normal reaction of the drum on the block. This is the radial force applied by the block on the drum. Similarly, we have the frictional force. This is the friction force on the drum as we have seen earlier, and this is the friction force on the block. These will be equal to mu into N. Now the distances are again A and L minus A. Now you can see that the line passing through the point of contact and the fulcrum are at the distance of B. So in this position we have to find out the braking torque and the force that can be applied to stop the drum. So let's proceed in the similar manner. Let's take the moment about the fulcrum point. You should always remember in brakes you have to take the moment always, whatever is the configuration given, you should always take the moments about the fulcrum point. So taking the moments about the fulcrum point, that is the moment about point O. This we have already seen, TB is equal to mu into N into R from the free body diagram of the drum. So taking moments about pivot point O, we have what are the forces? N, F and P. So N into distance A, again N will be rotating in the anti-clockwise direction, so it will be positive, so N into A. Then we have F, this F will be again rotating this in the anti-clockwise direction, so it will be again positive. The distance of the line of action of the frictional force F from this fulcrum is B. So the moment of friction force F will be F into this distance B. So this will be mu N into B. Similarly, again we have P. So P will be again rotating this lever in the clockwise direction about the point O. So this will be negative. So it will be taken on the other side. So the moment of P is P into this distance L. So this will be the equation of moment. So from here we will try to find out the value of N. We will take N. N is common here in both these. So we will take it outside. We can write this equation like this. So from here we can calculate N. N is equal to PL upon A plus mu B. So this value can be put in the equation of braking torque. So we can get the braking torque as TB is equal to mu PL R upon A plus mu B. This equation will also give us the value of P, the value of load that should be applied to stop the drum. That is given as P is equal to N into A plus mu B divided by L. This is the equation for load applied. Now, this was the case when the drum was rotating in the clockwise direction. Now suppose in the similar position of the fulcrum, if the drum is rotating in the anti-clockwise direction, then what will happen? So let's see it. This is again the drum, then you have the lever, then you have the distance B, the line passing through the point of contact is at a distance B from the fulcrum. Then these are the forces will be same, only the frictional force will be changed. So the normal reaction will be same as earlier. Now since this drum is rotating in the anti-clockwise direction, so the velocity suppose at this point will be in this direction, means towards left. So the force of friction in this case will be acting on the right direction. As the drum is rotating in the anti-clockwise direction, this will be the direction of rotation of drum. So force of friction will be acting in the opposite direction, that is towards right. So this will be the direction of force of friction on the drum. So force of friction on the block will be in the direction opposite to the force of friction on the drum. So this will be the force of friction on the drum, right? So, and both the force of friction will be equal to mu into n as per the Coulomb's friction. Now again the distances are a and L minus a. Now let us try to take the moment about the point O. Taking moment about the point O, N will again rotate this lever in the anti-clockwise direction, and the moment of force N will be N into distance A. Now P will again rotate in the clockwise direction, so moment of P will be P into L negative. Again we can see this, the moment of force F in this case will be in the clockwise direction. This force F will move this lever in the clockwise direction about the point O. So the moment of force F will be force F into this B in the clockwise direction. So it will be negative. So the equation will be something like this. N into A in the anti-clockwise direction will be equal to P into L in the clockwise direction plus F into B in the clockwise direction. So this will be the equation of moment. From here again we will try to find out the value of N as done previously. So N will be equal to, this will be taken on this side, mu NB will be taken on the left side. So N into A minus mu B will be equal to PL. So N will be equal to PL upon A minus mu B. So what is the difference? This difference is just the sign of the friction force. So this frictional force is just changing the sign. So N will be equal to PL upon A minus B. Here N was PL upon A plus mu B. Here the N is equal to PL upon A minus mu B. So this will give us the torque as TB is equal to mu PL R upon A minus mu B, and similarly this will give us the value of applied force P as N A minus mu B upon L. This is a very significant equation and we have some outcomes from this equation. So let's see them. So this was the situation. The drum is rotating in the anti-clockwise direction and the line passing through the point of contact is at a distance of B from the fulcrum point. So in this situation we obtained the equation of P as N A minus mu B divided by L. Now in this equation, if suppose A is equal to mu B or A is less than mu B, if A is equal to mu B, then what will happen? P will become 0 or P will become negative if A is less than mu B. And what this implies? This implies that the force needed to apply this brake is virtually 0. That is, once the contact is made between the block and the drum, the brake is applied itself. This means that no external force is required to apply the brake, and hence this brake is known as self-locking brake. Self-locking brake are generally not desired. Now next, here we had this equation NA is equal to PL plus mu N into B. PL is the moment of the force P that is applied on the lever, and mu N into B is the moment of the frictional force. In this equation NA PL plus mu N into B, what we see here? We see here that the moment of the force P is aided by the moment of the frictional force. That means the moment of the frictional force is aiding the moment of the applied force. What does this mean? That the frictional force is actually helping the applied force. So this implies that the force P required to apply the brake decreases due to the frictional force. Or in other words, the frictional force helps to apply the brake. So this type of brakes are known as self-energizing brake. So we observe that the friction force mu N is in the same direction as that of the applied force. So we can see that the friction force aids in applying the brake. Both are in the same direction. This is also rotating the lever in the clockwise direction, and friction force is also rotating in the clockwise direction. Both are in the same direction, so the friction force is helping the applied force. So these are self-energizing brake. Practically, we wish to have self-energizing brake and we generally avoid to have self-locking brake. But In some cases, self-locking brake are used. They are used in backstop of rotating parts. So this is all for today's lecture. We'll continue this lecture and discuss the another configuration of this single block brake. I hope you have understood up till now. In case of any doubt, please feel free to contact me. Thank you.